So what have you seen of Newton's laws so far? Have you seen how each one of them is actually stated usually?
Yeah.
So what is, for instance, the first one or the second one or the third one?
The first law is an object that's in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted on by a force.
Right. Although it's often much easier to write that just as an equation, and then you can get all the information you need from that equation. The unless acted on by a force, we could talk about that in terms of what happens if there isn't a force. If there is no force, the net force equals 0. What would happen to an object if there's no force?
It would just stay at rest or stay moving.
Yeah, it continues doing what it was doing, either staying at rest if it was already at rest, or staying in motion in the exact same way if it was already in motion. Specifically, what about it is not changing if the net force is 0?
Acceleration.
I would say velocity. Not that the acceleration is not changing, but that there is no acceleration at all. No force means no acceleration. So Newton's first law can be phrased like this: net force equals 0 if and only if acceleration is 0. In other words, v is constant. Alternatively, you could say momentum is constant because mass is generally assumed to be constant, so mv will also be constant. But note that then if and only if statement like this, if and only if works in both directions. If and only if means if the net force is 0, then the acceleration is 0. And also, if the acceleration is 0, then the net force is 0. So these are either both true or they're both false. Any questions on that so far? And one useful way we can actually apply this is in any situation where you know the object is not accelerating, then you know that the forces on the object have to add up to 0. So this is useful for setting up equations about the forces. And also the other direction. If you know all the forces on the object and you know they happen to add up to 0, then you know the object is not accelerating. The velocity must remain constant. Either it's traveling in a straight line with the same speed forever because there's no acceleration, or that same speed might be 0. Maybe it's staying at rest forever. But I want to emphasize that although we in language, we make a distinction between object at rest stays at rest and object in motion stays in motion in the same way, those are really describing the same scenario. Those are just describing an object whose velocity is constant. And it's just that in the case of the object at rest, that constant velocity happens to equal 0, but it's still a constant velocity. Any questions on that first law so far? And yeah, the second law can be written as an equation as well. Net force equals mass times acceleration. And this one's not exactly an if-then statement. This one's true in general. For any object, the net force on the object must equal the mass of the object times the acceleration of the object. I guess this is technically kind of an if the mass is constant, then this is true sort of thing. But I don't think we're really looking at any situations where the mass is changing. More generally, we could also think of this as net force equals the rate of change of momentum, change in momentum over change in time. So you could think of the total force acting on the object as telling you how fast the momentum of the object is changing as time passes. Or alternatively, you could think of the total force as causing acceleration. And the mass in that case could be thought of as the level of difficulty. More mass means it takes more force to get the same acceleration. And I think one of the interesting things about this is that the second law kind of includes the first within it. Because for the second law, if you assume you already know F net equals mass times acceleration, what would happen to this equation if you replace acceleration with 0?
It would become the first equation.
Yeah. The second law includes the first law, sort of built in within it. So this is, the first law is not really separate information. If you already know the second law, you don't actually technically need the first law. The first law is already implied by the second law. So I'm not sure why they're usually listed separately. The first law is really just a side effect of the second law. It might just be that people like things that come in threes. But if you just had Newton's second law and Newton's third law, Newton's first law is automatically implied by that anyway. So it's not really a separate thing. It's just that we are often dealing with cases where the acceleration is 0. So it's sometimes useful to think of this as its own law anyway. Any other questions on that so far? And this also means that we can use this to set up equations as well. Much in the same way that if you know that the object is not accelerating, then you can add up all the forces and set that equal to 0. If the object is accelerating and you know its acceleration, you can multiply the mass of the object times the acceleration and set the total force equal to that mass times acceleration. So this is still useful for figuring out force diagrams, but specifically if you're talking about an object that is accelerating. Usually we tend to think of statics problems as an object that's not moving. But technically this is true not only for objects that are moving, but for objects that are not accelerating. So if you have an object that's moving but at a constant velocity, you can still say the forces on that object add up to 0. If the object is moving at a changing velocity, if it's accelerating, then you can still figure out something about the forces. You can say the forces have to add up to mass times acceleration. So this can also be useful for setting up free body diagrams. And typically that would be called a dynamics problem rather than a statics problem. Dynamics in the sense that it is moving, it's changing as time passes. But this is often useful in situations like, let's say you've got an object or a collection of objects in an elevator that's accelerating upwards. Not just moving upwards, but accelerating upwards. If you know the acceleration of the entire elevator, then presumably everything in the elevator is also accelerating at that rate. So for each object in the elevator, you can multiply the mass of that one object times the acceleration of the elevator that it's in, and that tells you the total force acting on that one object. Any questions on that so far? And of course, that also works in reverse. If you know the acceleration and the mass, then you know what the forces have to add up to. But also, if you know all the forces and you can add them up, then you know what the acceleration is, assuming you know the mass. And the third law is a little different because it's not really just talking about total force on an object and how that relates to motion. Third law is more talking about a pair of objects and how they're interacting with each other. And how have you usually seen the third law described? What are some wordings you have seen for that?
It was like a pair of objects exert an equal and opposite force on each other.
Yeah, anytime you're talking about a pair of objects interacting, because that's really all a force is. A force is an interaction between a pair of objects, specifically the sort of interaction that can cause acceleration. But an interaction between a pair of objects, if you just have one object, there can be no force. A force is between an interaction between two or more objects. And you can say that each one of those objects feels a force from the other. Like for instance, let's say if I'm like leaning on a wall, I'm exerting a force on the wall to the east. The wall is exerting a force back on me to the west. So those forces are the same magnitude. Force of my hand on the wall and force of the wall on my hand are equal in magnitude but opposite in direction. So if I'm standing here leaning on this wall, then the wall is experiencing a force from my hand, force on the wall from me. But also my hand is experiencing the same amount of force in the opposite direction. That's the force on me from the wall. So Newton's third law is just saying that forces have to come in equal and opposite pairs like this. You can't just have a force in isolation. Of course, if you're looking at a free body diagram of just one object, this doesn't really apply because Newton's third law is talking about forces between pairs of objects. So if you're looking at just me, then there's the force on me from the wall and that's it. Or if you're looking at just the wall, then there's the force on the wall from me and that's it. But if you consider both objects, then you'd have to have this, the force from the wall on me and also the force from me on the wall. So those are the equal and opposite pairs of forces that Newton's third law is talking about. So there's a lot of ways this is phrased. The traditional method of describing it is usually for every action there is an equal and opposite reaction, but I find that's a really confusing way of saying it. I usually just think of it as forces come in pairs. That A exerts a force on B and B exerts the same force in the opposite direction back on A. So I would think of this as forces come in pairs. And also we can even describe this one as an equation as well. Specifically, we could say the force of A on B is, how would we describe opposite direction but same magnitude mathematically?
With a negative.
Yeah, a negative sign means take the exact opposite direction. So the force of A acting on B is the same as the opposite of the force of object B acting on object A. If we treat A and B as just the temporary names of the objects. So the force that object A exerts on object B is the exact opposite of the force that object B exerts on object A. That's all Newton's third law is talking about. And this is true for any force, even forces that we tend to think of in isolation, like for instance, gravity. Gravity is pulling me down, but that's gravity on me from what other object? When I say gravity is pulling me down, what's the actual physical object that's pulling me down using gravity? Gravity of what?
The Earth.
Yeah, the Earth itself. So when I say gravity is pulling me down, what I'm really meaning is Earth is using a gravitational force to pull me down. So if you consider both of those objects, Earth and me, if you consider each one of these as a free body diagram, like if you treat me as just a single point, and if you treat Earth as just a single point, the force of gravity on me is towards the center of the Earth. So this would be force of gravity on me from Earth. And that's just going to be my weight, mass times acceleration of gravity, mass times 9.8. But meanwhile, what's the Earth itself experiencing?
An opposite force exerted by the person.
Yeah, the Earth is experiencing a force in the opposite direction, so that'll be upwards. And same magnitude. Newton's third law guarantees that these forces will be the same magnitude but opposite direction. Effectively, because I would just think of these as the same force viewed from two different perspectives. This pair of forces is just the interaction between, the gravitational interaction between me and the Earth. It's just that this downwards arrow is what that interaction looks like from my perspective. This upwards arrow is what that same interaction looks like from the Earth's perspective. So this would be force of gravity on the Earth from me. So my gravity, my mass is exerting a gravitational force that's pulling the whole Earth upwards. But does the Earth noticeably drift upwards as a result of me falling downwards? Not noticeably. And why is that? If we're both experiencing the same force, why do I, like if I step off of a curb, why do I noticeably fall towards the Earth, but the Earth does not noticeably fall upwards towards me? What's the big difference there?
Is it because the Earth has a lot more mass?
Yeah, this is all about mass. In fact, if you take a look at, going back to Newton's second law, mass times acceleration, if we write out these forces, we can assume from Newton's third law that the force on the Earth has the same magnitude as the force on me. Because again, it's the same interaction, just viewed from two different perspectives. Each one of those forces can be said equal to mass times acceleration, though. So the force on me is equal to the mass of me times the acceleration of me. But the force on the Earth is going to be the mass of the Earth times acceleration of the Earth. And what do we know about mass of the Earth? Yeah, it's very heavy. The Earth's mass is enormous. So we're going to have the enormous mass of the Earth. And if the mass is very large, what does that suggest about the acceleration? Yeah, we're going to have, right, a very large mass times a very small acceleration. So we've got a medium mass times a medium acceleration balanced out by a large mass times a small acceleration. So if I step off a cliff and start falling, I'm falling downwards towards the Earth with a very large acceleration. The Earth is also falling up towards me, but at a very, very small acceleration. So small it wouldn't even be noticeable. Because if you wanted to solve for this acceleration, first of all, the acceleration of me would just be 9.8 meters per second squared. If I'm in free fall near Earth, that's my acceleration. If you wanted to find the acceleration of the Earth, how would you isolate acceleration of the Earth here?
You could divide the other side of the equation by the mass of the Earth.
If we divide both sides by mass of the Earth, that means the acceleration of the Earth will be 9.8 meters per second squared times my mass divided by the Earth's mass. And that fraction of masses is going to be so small it basically rounds off to zero. So the Earth is technically accelerating upwards as a result of me attracting it gravitationally, but not in a way that would be even noticeable to any equipment we have. And also, I'm not the only force acting on the Earth. There are other forces all over the place that are much stronger than that. So those would be much more noticeable. For instance, even the sun's gravity would be more significant in that case, even though it's far away. Any other questions on those Newton's laws so far? Oh, and F normal, there would also be a normal force if I'm standing on the Earth. If I'm just sort of near the Earth, like let's say I just stepped off a cliff and I'm currently falling, then that would mean that there is no normal force. There's only the gravitational force. If there is a normal force, though, that would presumably be, I'm not falling. If I'm just standing on the ground, I'm not falling because, yes, there is a normal force. So that would be the normal force on me from the ground, which is also just part of the Earth. Would those two forces be the sort of pair that Newton's third law is talking about? Are these the equal and opposite forces of Newton's third law? Are they the force of A on B and the force of B on A? They do cancel out, but keep in mind Newton's third law is about a pair of forces between two different objects. Newton's third law isn't just about any pair of forces that happen to be equal and opposite. Newton's third law is specifically about the force of A on B and the force of B back on A. And that's not what's going on here. These are both forces on me. It's force of the gravitational force on me and the normal force on me. So since they're forces on the same object, that's not what Newton's third law is talking about. Newton's third law is talking about force of A on B and force of B back on A. So for instance, the force of gravity on me from the Earth is paired with the force of gravity on Earth from me. These two would be a Newton's third law pair, because that's the sort of pair we're talking about here, the interaction between two objects. But the force of gravity on me and the force of the normal force on me, that's not Newton's third law. They do cancel out, but why do they have to cancel out? How do we know that the normal force is exactly enough to cancel out gravity here? Why would we expect those to be canceling out? Yeah, you're not flying up, you're not sinking down, there's no acceleration. And which one of these laws is talking about what happens if there's no acceleration? Yeah, the first law. The first law says if there's no acceleration, then the forces add up to zero, the forces on that one object. So these two forces canceling out is really more about the first law. The fact that I am not accelerating, I'm just standing still, that tells me that all the forces acting on me have to add up to zero. So these are really more related by the first law than the third law. Or if I was accelerating, then they'd be related by the second law instead. And also note that the normal force doesn't have to be the opposite of the force of gravity. It just happens to be the opposite of the force of gravity because those two forces add up to zero. But it's entirely possible to have a situation where they don't. Like for instance, let's say there's a rope here and I'm holding onto the rope and supporting some of my weight by leaning on the rope. That way, I've got an upwards tension force from the rope and an upwards normal force from my feet. Those together would add up to my weight. But in that case, neither one of them, like if I've got a normal force and a tension force from a rope that I'm holding onto, the normal force would actually be weaker than the force of gravity because it's being assisted by the rope, assisted by the tension force. Or alternatively, let's say I'm bracing myself against the ceiling, pushing up on the ceiling. That's going to mean that I've got a normal force and also, now I've got a gravitational force pulling down, and also the ceiling itself is pushing me down if I'm bracing against the ceiling. So in that case, the normal force would be stronger because it's acting against not only gravity, but also the force from the ceiling as well. So the normal force doesn't have to be the exact opposite of force of gravity. It just happens to be in this case where they're the only two objects or only two forces and the object is not accelerating because the forces have to add up to zero if the object is not accelerating. So these forces are related by the first law. These forces, force of me on the Earth and force of the Earth on me, those are what the third law is talking about. And also one other thing, if there's a normal force of the Earth pushing up on me, what other force has to be included by Newton's third law? If the ground is holding me up, then also I'm doing what? Yeah, I'm pushing down on the ground. So there's also a downwards normal force on the Earth from me. My feet are pushing down on the ground. And separately, these would be a third law pair. The normal force on me from the Earth upwards and the normal force downwards on the Earth from me. These two forces would be a third law pair because they're force of A on B and force of B on A, two objects interacting with each other. And this is useful. The third law is useful if you're dealing with a system with several objects, especially if you've got like several objects and you want to draw a free body diagram for each one. As soon as you include a force on one object from another object in the system, make sure you also include its equal and opposite on the other object. Like for instance, if you've got two books stacked on top of each other, book one, book two. Book two is pushing down on book one, and book one is also pushing up on book two. So each one of those free body diagrams should include that force. Book 2 on the top experiences an upwards force from book 1. So make sure you include that on the free body diagram for book 2. But also underneath, book 1 experiences a downwards normal force from book 2. So make sure you include that on the free body diagram for book 1. Any other questions on Newton's laws so far? And you mentioned capacitors earlier. Was there a specific capacitors problem you'd like to try out?
Actually, I was wondering if you could review like the different exponential relationships, like for Q and I and V.
Yeah, there isn't really one overall equation for each one. It's more that I think it would be more useful to just know how to construct exponential equations in general. Because anytime you've got some sort of exponential growth or decay pattern, or let's say decay, because decay is what we're talking about in all these situations anyway. Anytime you know you've got exponential decay, usually what are the most important values to know in any exponential decay situation? Like let's say we're talking about time versus, let's say, I don't know, maybe charge. If you wanted to draw a graph of an exponential decay situation as charge is decaying, what would be the important values on the graph to know? Yeah, you want to know how much charge there is initially. So let's say you know that. And in fact, let's say we know, let's say initial charge is 20 coulombs. And what else would you need to know? How much there is to start with, and also that's really more, the capacitance is really more specific to the situation. I'm talking about more in terms of any exponential decay situation. Presumably the value starts at some value, let's say 20 coulombs. Half-life is really about how fast it's decaying, right? So let's say we know the half-life also. Or maybe we don't necessarily know the half-life, but the half-life is going to be important information. So maybe we know the half-life, maybe we don't. Or alternatively, the time constant. The half-life and time constant are really the same information, just written in different formats. They're both talking about how fast the decay is happening. But if it's decaying, presumably it's decaying towards some final value, some value that it's approaching. And that's another important thing to know. Typically in any exponential decay situation, I would want to know what value does it start at, and after a long time, what asymptote is it approaching? Let's say after a long time, Q approaches, let's say 4 coulombs. So let's say it starts off at 20, and then after a long time, it's getting closer and closer to 4. Let me actually mark that on the graph then. So if we have a value, and I'm calling this Q because we might be talking, for instance, about charge of a capacitor that's discharging. But let's assume that this Q could be anything. We just have some value Q that changes as time passes. And we know that it starts off at a value of 20. It approaches an asymptote of 4 as time passes. And if we don't care too much about how much time it takes, that's most of the information we need. And we can actually use this to write out most of the equation. If you want to write out an equation for this, Presumably we want Q as a function of time. This is, assuming this is an exponential decay equation, what should our equation include? It's going to involve Q initial, but that's just one of the values we can plug in eventually. I would start with the e to the something, yeah, because the most important thing about this graph is that it is exponential decay. The exact values, the exact shape, the exact parameters we can fill in later. But the most important thing is that this is an exponential equation. So this is going to involve e to the something. Presumably e to the something about t. And we don't know what the multiplier is yet, so I'm just going to call that lambda for now. Let's just say this is e to the lambda t. This is exponential decay. It is approaching some asymptote. And by the way, it doesn't matter if it's approaching from above or approaching from below. As long as it's getting closer and closer to some asymptote, that counts as exponential decay. Whereas exponential growth would be if it's spreading out away from the asymptote, whether spreading out above or spreading out below. So for instance, these curves both count as exponential growth. These curves both count as exponential decay because they're both approaching some asymptote. The difference between the value and the asymptote is getting smaller. So since this is exponential decay, we can assume it's e to the power of some negative number t. I'm just going to write that as negative lambda t, where t is some positive constant that we don't know yet. Also, this is presumably going to be possible to multiply by some value. For instance, you could multiply by any value, and this would still be exponential as long as it's constant. So let's say times k, where k is some unknown constant. Also, as we have it written here, as t gets larger and larger, what's this value going to approach? If you've got e to a more and more negative power, what does that get closer and closer to as t gets larger and larger? Yeah, that's going to approach 0. So this whole thing goes to 0. The limit is 0. But we don't want it to approach 0. We want it to approach 4 instead. So how could you take a graph that approaches 0 and change it so it approaches 4 instead? How could you just take that whole graph and shift it up 4 spaces? What would you have to do to the equation to make the whole graph shift upwards? Yeah, we just have to add 4. Or more generally, add whatever the value of the asymptote is. So let's say plus, I'm just going to call this q sub infinity, because it's the value of q after infinite time, after a very, very long time. So this gives us the asymptote. So in general, we can write any exponential decay equation as the function equals some constant times e to the negative lambda t, where lambda is some unknown constant, plus the value of the asymptote. And what this ultimately does is the k times e to the negative lambda t tells you how far you are from the asymptote. That is the value that's decaying as time passes. So this value is k e to the negative lambda t. And then there's also this extra plus 4. So k e to the negative lambda t is shrinking towards 0, but we're adding 4 to each of those values to give it a new asymptote. Any questions on that equation so far? So this is generally the format I would start with. We know it's going to be exponential decay, so e to the negative lambda t. You could stretch or compress that any amount you want, and it would still be exponential decay. So you could have times a constant to stretch or compress it. Also, this constant, if this constant were negative, what would that do to the graph? Like if you take a function and multiply by a negative, what does that do to the graph? Yeah, that's going to invert it. It flips it upside down across the axis. So that's what allows you to have exponential decay coming up from below, approaching the asymptote from underneath. That would be what happens if you have a negative multiplier here, whereas a positive multiplier means it's coming down from above. So you can get most of this equation just from what's the starting point and what's happening after a long period of time. So in any situation where you expect it to be exponential decay anyway, like capacitors or a tank of water that's gradually draining, or a hot object getting colder as the heat drains off to the environment, anytime you expect exponential decay, I would start by focusing on what's the value at the beginning and what's the value going to approach after a long time. That gives you an initial value and an asymptote. The asymptote is just going to be the plus whatever here. And let's see if we can find that k value as well. If there's no asymptote, if the whole thing is approaching 0, then the k value will just be the initial value. But more generally, if there is an asymptote, let's try this out. If we fill in these values, let's say specifically times 0. Let's fill that in. Q of 0, if we just replace t with 0, we get k times e to the negative lambda times 0 is just 0, plus the asymptote. And we can fill in some of these values. What do we know about the initial value here? Yeah, the initial value here is 20. K we don't know yet, but what's e to the 0? 1. Anything to the 0 is 1. And what's our asymptote in this case? Yeah, 4. So if you solve this for k, what do you get? Yeah, should be 16. And what does 16 mean on this graph? What's important about the value 16? We got that 16 from 20 minus 4, right? What's important about 20 and 4 on this graph? What would the difference between 20 and 4 signify on that graph? Yeah, how much difference there is at 0 seconds. At the very beginning, we've got a value of 20, and we know we're eventually going to approach an asymptote of 4. So the k value, the multiplier there, really just represents that initial difference. It represents how high above the asymptote you start. Or if you started below the asymptote, you'd have a negative value for k, which is why it would be approaching upwards from below. But that's generally how you can interpret k here. K is the difference. In fact, you could even write that symbolically. K is the difference between 20 minus 4, that was just q initial, minus the limit, q infinity, the asymptote. So the multiplier here is just the initial value minus the asymptote. So I think that gives us essentially a general formula here. We've got initial value minus asymptote times e to the negative lambda t plus asymptote. And that'll work for any exponential decay function. And we know the initial value, we know the asymptote. The only unknown left is what? What's the only thing we would still need to find here? Yeah, the lambda value. And the lambda value ultimately relates to how fast it's decaying. So the initial value and the asymptote alone can't tell you lambda. They can tell you the plus whatever, they can tell you the multiplier, but lambda requires one more piece of information. You need to know something about an intermediate time between beginning and after a long time. For instance, maybe you know the half-life. You know how much time it takes to decay halfway towards the asymptote. Or maybe you know the time constant. Or maybe you just have one more data point. Maybe you know that after 3 seconds, it has decayed to 8 or something like that. As long as you know one more piece of information about what's happening at some other time between 0 and infinity, then you can figure out what lambda is. So let's try that out. Let's say our one more piece of information is, let me tighten this up a little bit. Let's say we know that it takes 5 seconds to reach q equals 8. So let's say that's our one more piece of information. We know that it takes 5 seconds. So we take a measurement at time 0, and we find that q is 20. We wait 5 seconds, we take another measurement, and we find that q has decreased to 8. Then we wait a very long time and find that q has approached 4, gotten really close to 4. So let's see what we can do with this. If we write out the equation we have so far, we got 16 times e to the negative lambda t plus 4. And we still need to find lambda. One way we can do that is by plugging in this one more data point. We can replace t with 5 and replace q with 8. Because at this time, t equals 5 seconds, q equals 8 coulombs. So let's try that out. If we just make that substitution, we can say when q is 8 coulombs, when t is 5 seconds. And now we have an equation where lambda is the only unknown left. So how would we solve that for lambda? Yeah, subtract 4. And divide by 16. 4 over 16 is 1/4. And then what else could we do here? Yeah, we're going to need to take a logarithm. One thing that's sometimes useful here is inverting both sides first. I mean, we've got a 1 over something. This could be thought of as 4 to the negative 1. And we've got e to a negative power. Before we take the logarithm, just to make the numbers easier to work with, I'm going to raise both sides to the negative 1 power. This is not necessary. You could do steps similar to this after you take the logarithm, but I think it's going to be easier to invert both sides first. 1/4 to the negative 1 is 4. And then on the right side, we can multiply the exponents and get e to the positive 5 lambda. Again, not necessary, but I think it's going to make the numbers easier to work with. And then, as you say, we take the logarithm of both sides. So logarithm of 4 equals, and then what's logarithm of e to the 5 lambda? Yeah, the logarithm and e to the power of cancel out because they're inverse operations of each other. So we're left with 5 lambda. Divide by 5, and that should do it. So that is the value of lambda. Lambda is logarithm of 4 divided by 5. And you could now fill that in for lambda. What I usually do is just leave it in terms of lambda, and then anytime I need to make calculations, I plug in that value. but filling in the actual lambda value can be kind of inconvenient. I usually just write it in terms of lambda and then write the lambda value off to the side. Or you could punch that into a calculator if you want a decimal approximation. And then you can use that, now that we have the entire formula, including the value of lambda, we can use this to predict how much there is at any time. We can say, what about after 7 seconds? Just plug in 7 for t and calculate q. That'll tell you how much is left. Why does it never reach 4 coulombs? Well, what happens as time gets larger and larger? Like if you plug in 1,000,000 for t, you get e to the negative 1,000,000 lambda. Is that going to be 0? Can you ever get to 0 by raising e to a negative power? No. E to any, like if you have e to the negative 1,000,000, that's the same as 1 over e to the 1,000,000. That's 1 over a very large number. So it's going to be very, very close to 0, but it's never actually going to get to 0. It just gets closer and closer as an asymptote. So this gets closer and closer to 0, but never quite reaches it. Plus 4, this whole expression gets closer and closer to 4, but never quite reaches it. More physically, it's because if we're talking about like a capacitor discharging, the capacitor is pushing charge out of itself. The more charge it has above and beyond equilibrium, presumably 4 is equilibrium here, the more charge it has above and beyond equilibrium, the more push it can create. But as it gets closer and closer to equilibrium, there's less and less push, so less and less ability to push more charge out. So it never quite gets there. Several equations for charging versus discharging. This one is really more the general case. This would work in general. As long as you know the value it starts at and the value it approaches, this should always work. And also, if you're specifically dealing with a circuit where it's just one resistor and one capacitor in a loop, lambda is always going to be 1 over RC. So if the circuit is just one resistor and one capacitor, and optionally one battery. So in a circuit with resistor and capacitor and optionally a battery, in one loop, lambda is always going to be 1 over resistance times capacitance. For more complicated circuits, that's not necessarily going to be true. But if the circuit is just one loop, one loop with a resistor and a capacitor, or even several resistors and several capacitors, as long as you can combine them into one equivalent resistance and one equivalent capacitance, then the lambda value here is going to be 1 over R times C. So this equation, I would say, is more general. You can set up specific equations for specific situations, but this one works for any exponential decay. In fact, if you remove the negative sign here, this would even work for, well, it mostly works for exponential growth. Instead of Q infinity, it would be the asymptote it's diverging from rather than converging towards. But I would say this equation in general works for any exponential decay situation. Any other questions on that? And again, start by looking at what's the initial value, what's it approaching after a long time. That allows you to find values of the multiplier and the plus whatever. And then if you have any one more piece of information about an in-between time, whether it's like a certain value at a certain time, or maybe you know the half-life, or maybe you know the time constant, you can piece together the value of lambda as well. And then you've got the whole thing. All right, that's all we have time for at the moment, but I will see you at the review session. Good luck on finals.
Casey.
You're welcome.